So, thank you very much for showing up. I want to tell you that it is a little bit of, it's difficult for me to give this talk because maybe some of you have noticed that yesterday I won a prize for science communication, which makes it very difficult to give a talk when you are now expecting a good talk. So hopefully you will see that I don't give good talks. I give the passionate talks that I feel evolve around the questions that I really think are some of the biggest questions. So I will tell you about my life as a citizen scientist, which we saw Trump before. I think one of the biggest problems that is sort of facing humanity is the question of fake news and the question of us not really trusting knowledge and science anymore. And I think one of the reasons that we don't trust science and scientific results and the scientific method is that there's a gap between researchers and normal people. So very often when normal people sit down there and I stand up here, I will talk very quickly. I will talk about very complicated things, and I will talk about how hard it is to understand. And I think what that does is that it builds a barrier between you and me. And what my work deals with is trying to break down that barrier, to try to show you that even challenges that are in the realm of something called quantum physics are approachable for you. I will talk about quantum physics, and I will not teach you quantum physics. I will not teach you to understand quantum physics because I don't understand quantum physics. Okay, but I hope that you will share my enthusiasm for quantum physics and what we can build if we understand how to play around with quantum physics. So, the question of citizen science is really, I think, one of the big questions right now because it deals with what is the difference between human intelligence and artificial or machine intelligence. Citizen science is a field that tries to seek out the most difficult problems that computers cannot solve and humans can solve. And they exist, which is very encouraging for us. And they also, the fact that they exist means that we can start studying how and why it is that we, in our brains, can solve problems that are very, very complex for computers. Because we often get this feeling that computers win all the battles that are going on at the moment. There's chess, there's Jeopardy, there's Go, and when you open the news, there's always a new field that has been revolutionized by artificial intelligence. And it always feels as if we are getting less and less sort of dominant. Some people, there's a futurist who's called Ray Kurzweil, has tried to predict what will happen in the future regarding artificial intelligence. So he's tried to sort of make a map of how long it takes for humanity to develop something new. And it looks as if it almost takes no time. And if you, on the other hand, just take computational power as a function of time, you will see that it rises very sharply. And at some point, he says in 2045, maybe on the 23rd of January, it will happen that humans will no longer be the most intelligent species on Earth. Which means that it's really fascinating that we live in a time, 10 or 20 years ago, we were undoubtedly the dominant species, and 20 years from now, we may actually be obsolete. Okay, so I'll just share with you some of the highlights that I have from sort of how good computers are, and I'll show you what has happened, because in the 80s, who was the most clever person, the smartest, the most intelligent person on Earth? It was the chess grandmaster, right? Because the most intelligent thing you could do was to play chess, except when a computer beats the grandmaster. Then it's actually not so intelligent to play chess anymore. Then what is most intelligent about us humans is that we can look at images and we can recognize them because we have this ability. Except that if you train algorithms, then suddenly they can see that there's a lamppost and a man and a skater here, right? But that's because that's not true intelligence. True intelligence is to be able to look at a picture and formulate a sentence that makes sense, right? Except that now we can merge computer vision with machine learning and language recognition, and then we can have something like this here. It's very blurry, sorry, but there's a cat here looking at a laptop, and this is maybe a little bit difficult to see, but it says a cat lying on a bed with a laptop, right? So now the computers can even look at pictures and formulate sentences that we don't recognize or don't recognize any errors in. But that's not true intelligence, right? True intelligence is being able to make sentences that make poetic sense to all of us, right? Writing poetry, except when computers start to write poetry that also sort of inspires us. Okay, so what is true intelligence is really to make a joke and be able to look in your eyes and tell whether you thought it was really funny or whether you were just smiling because you were polite, right? That is true human intelligence, except if you have 3 million face videos and you can train that with an algorithm, and then you can suddenly develop an app that can look at you and tell you what you are feeling, what you are sensing. Right? So the future of this is that we will all soon be wearing glasses, and those glasses, they will be telling us when there's a joke that those people actually didn't understand it, so you have to tell it a little bit differently. Or maybe when we have some online learning systems, it will see that we are getting bored, and it will speed up the process of learning for us. So I think that's really sort of a fantastic advance. Computer games is one of the topics of this, so I'll just quote one of my favorite topics, and that is Google DeepMind a couple of years ago took a lot of old 80s games and tested their DeepMind algorithm on this. And so one of the games was called Breakout, and in the beginning, of course, it couldn't play it, and then after a little bit of time, 240 minutes, it found out that you just have to sort of hit a wall, hit a hole here, and then it will just bounce back and forth, and then it solved the problem, right? So I told you before that we are in a unique time in our history, and this curve is the proof, because there are 35 games here, and the computer solves 20 of them the best, and the rest are solved best by humans, which means we are in this very fascinating intermediate time. Soon, computers will be able to do everything. Some people say. Others say, and they are also artificial intelligence researchers, and more of them, when I talk to them, and they are not quoted in public, admit that developing true artificial intelligence is very difficult. And some of them have actually gone public, although it's not very popular. So he says, Gary Marcus here, he says, asks the question whether the current paradigm of using big data analysis is really something that will take us to true human-like intelligence. And what he says is no, because what is truly human-type intelligence is the ability to have very little data and make intuitive decisions that for some reason are very likely to be right. So what he says is that if we want to develop really true human-scale artificial intelligence, then we need to study ourselves. We need to study psychology. And that's what I will talk about today. So I'll talk about one of my inspirations. I'm a quantum physicist, so why do I talk about all of this here? When I was 10 years old, I was sitting in a clover field with my 2 sisters, and I wanted to tease them. So I said, I will now close my eyes, and then I will pick up a 4-leaf clover. So I didn't see a 4-leaf clover, I just said it for fun, and then I closed my eyes, and I picked it up, and it was a 4-leaf clover. And I really didn't understand why, because I promised myself that I hadn't seen it, right? And I keep thinking about what it was. And of course, my subconscious mind had seen that 4-leaf clover and told my conscious mind to make a joke because it would be a good joke, right? So there is a lot of power in our subconscious mind. And I just want to share with you the 3 favorite examples that I have of this, of human ability to solve something which is very complex. I'm a physicist, so one example is catching a ball. Have you ever thought about how you catch a ball? The way you catch a ball as a physicist is that there's something in Danish it's called the skråkast. So you solve Newton's equations, then it becomes a parabola, right? But there's also something called wind resistance, which goes as v squared, which makes it a little bit more complicated. And then there are the wind conditions, which means that a physicist will say, I cannot actually not calculate it. So I don't know how to do it. But we all catch the ball. And why do we catch the ball? What we found out, or psychologists find out, is that we have an algorithm which says, move such that you keep the angle to the ball constant. And if you do that, you catch the ball. Try it tomorrow, and you will not catch the ball because you're focusing on that algorithm, but it is what we are doing, okay? So this is what we're doing. We are finding something, and that has nothing to do with wind resistance and with the wind conditions. We just catch the ball because we found out what the essence of it was. We humans are unique in one way, and that is that we are limited. It is fantastic to be limited in one particular way, our storage capacity, also called our minds and our memories. So I often tell that to my wife when I forget things, that this is really our best ability. And why is it our best ability? It is our best ability because we learn how to filter data, filter important from unimportant data. And one psychology professor in Germany found out this because he took a study in which he said 2 American cities. And then he had lots of college students from the US, and he had German university students determining which of the 2 cities was the bigger one. And who won? The Germans. And why did the Germans know the American cities better? He didn't know, but he asked them around. And then he asked the Germans, what did you do? They said, in the end, they said, I don't know, I just picked the one I had heard about. Right? And the Americans had heard about all of the cities, which means they didn't have this filtering algorithm. So that's an example that sometimes being limited in your cognitive abilities can actually be a benefit. And I think that's very comforting. Right? So, yes. So my favorite example is this. It's a set of gears that are connected. And the first one turns counterclockwise. And your task is now to tell me how the last one turns. So this was a psychology result, and I see some of you people doing something like this, right? And that's exactly what the students, so it was children who were being studied, and they did exactly like this, except they had their tongues out, so they did like this, right? So they did this, but then at some point, they found out something different, another way to solve it, right? You could just say A, B, A, B, A, B, or you could count whether there was even or odd, and then you would know it. And the fantastic thing was, in the second that they discovered this, their eyes did like this. So they had an outwards reaction to the inwards process of getting a new idea. Okay, so if they are very clever psychologists, then they will make a new game in which at some point there's a star here and a star here and a star there and a star there, and they will try to make the children's eyes do like this and like this and like this and like this. And they did it. And the children discovered the algorithm. And if you don't think this is fantastic, go away, because that is fantastic. This means that we can start to influence the conditions of getting new ideas just by stimulating us from the outside. It just shows that there's a wonderful world inside of our mind. Okay, how can we take advantage of that? My idea is to take some of the well-spent or not so well-spent hours spent playing computer games. And if you just want to compare sort of this big block here to the small block here, which is the time spent producing Wikipedia, then, so we could all stop playing computer games 1 week, and then we could produce 30 Wikipedias. So that's a big, big number. And if we could make games that made good things, that would be a good thing for humanity. Right? So that's what we are doing. One of the good guys in this field is called Louis von Ahn, and he has a site which is called gwap.com, gameswithapurpose.com, and his mission is to map all images on the internet and label them. So you can have a game, and you can play them, and you can map all of the different images. There's also a place which is called zooniverse.org. At zooniverse.org, it started being galaxyzoo.org. It was a poor PhD student who had lots and lots of galaxies that he had to characterize in 2 different shapes. And it was very easy for him. He had just to look at it and say, okay, this is a spiral, okay, this is an orbit galaxy, and then so on. But he could see that he had so much data that he would only finish it at the end of his PhD doing all of the categorization. So instead, he made a website in which people could go in and help him, and it took a week for everyone to help him and do the whole thing. And that evolved into a site, which is now called zooniverse.org, and you can go in there and you can help researchers by classifying various different things. You can search for extra solar galaxies. You can search galaxies. You can look at the sea floor. You can, if you're biologically inspired, then you could help the researchers look at bloodstains and look for cancer cells. And you can really sort of, using your pattern recognition skills, help researchers. You don't need that much skill in order to do it. So if you want to be a little bit more challenged, then you can try a game which is called Foldit. Has anyone heard about Foldit? A couple of people. Yes, very good. So Foldit is a cool game. It is the problem of finding out how proteins fold in nature. It's very important to understand how proteins fold in nature because that determines how our metabolism works. And if we want to understand diseases like HIV/AIDS, this is very important. But we don't know how to calculate because it's all of these amino acids, they're connected in different ways, and there's so many different forms and shapes that it could take. Our computer algorithms will never finish. So what they have done is they have made a game. So it looks like this, and then the idea is that you get to rotate these things around and find these good places. So this here is a conflict because these two are sort of repelling each other, so you rotate there and now it's better. But at some point these proteins become so complicated that no matter what you do, then it's bad. So what actually happened in this game was there was a 15-year-old high school kid in the US who had fantastic results and they filmed him. So the researchers filmed him and it turned out that he did something which was stupid or bad, and then he did something else which was also bad, and any intelligent algorithm would now discard that solution, but he did something third, and now it was suddenly much, much better. So that means that he had discovered an algorithm that the intelligent computers couldn't find. So our attempt of doing this is called science@home.org. 200,000 people have been in there and playing the games, and I'll tell you about the results in just a little while. So what we're trying to build is something called a quantum computer. And for you who don't know what this is one of the earliest computers. So computers have gotten smaller and smaller and smaller as time goes by, and that's because these transistors, they're called, inside are smaller and smaller, and that is called Moore's law. So Moore's law just says we get better and better computers as time goes by. But at some point we get into this regime, and that's right now, where these transistors are so small that the electrons that are going here actually start to jump from one place to the other because of something called quantum physics. So we're getting into this quantum physics, which means that we cannot produce smaller and smaller computers and faster computers. So instead, we're saying, let's use these laws of quantum physics instead. And one of the very strange properties that I don't understand is that atoms and quantum particles can be at two different places at the same time. So in order to understand that, people find sort of analogies, and one of the analogies is what is called Schrödinger's cat's example. So the example is a fairly sort of morbid example because there is a radioactive atom here that when that one atom decays, then it crushes a vial of poison, and then the cat which is inside of the box dies. And then you close the lid and time goes by. And you don't know whether this one atom has decayed or not. And quantum physics says that it has then both decayed and not decayed, which means that the cat is both alive and dead at the same time, which is very, very strange. And we still discuss sort of what that really means, because we don't agree about that. But we do agree that this could be very useful. It could be useful in what is called a quantum computer. We need to use atoms then, and just sort of to realize what atoms are and how small atoms are. I've sort of looked the internet and then found smaller and smaller images of a grain of sand. And at some point we get into this place where we have the individual atoms. So how small is an atom? An atom is so small that if I take a single grain of sand, then there are more atoms inside of that one than there are grains of sand on Earth. Right? So take a handful of sand and start counting all of the grains of sand you have in your hand, and then you get an idea after a couple of hours how many atoms there actually are in the world. So they're very, very small. But now we want to use this for a quantum computer, and I need to sort of make I can see 2 or 3 people falling asleep, so I need to make a small exercise now. So I need all of you to think of either your left hand or your right hand. Either your left hand or your right hand, okay? And And don't show it yet. Sorry, don't show it. Okay, but so now I'll start with you, right? So you have either, don't show it yet, a right hand and a left hand, right? So you have two different possibilities. So how many do we have if we have now the two of you? So I call this 0, I call this 1. How many do we have? Then we have 4, right? So then we have 2 right hands, 2 left hands, and 1 of each, right? So if we take you then it sounds very good to say 2, 4, 6, but it's actually 2, 4, 8. And that's because we have all of your 4 solutions coupled with a right hand, and all of your 4 solutions coupled with a left hand. 8, right? And that means that this is the power of combinations. That every time we add one of you, then we get twice as many combinations. So the idea is now to try to show what would happen now. So what would happen if we had 300, roughly 300 atoms, 300 people in here? Then we actually have more possibilities of different raising of our hands than there are atoms in the known universe. So it becomes a huge number with just 300 people in here. So now, okay, let's try to make something slightly fun. So I will have a line here, and then all of you, please raise the hand that you had thought of if you still remember. Okay, like this, not you. Okay, very good. So have a look around and see then. So if we said this was a 0 and this was a 1, then all of you are representing now one big string of 0s and 1s, right? Okay, down again, and then now you wake up and your turn to do your hand, right? And it's not mathematically possible that it's the same combination, but very close. Okay, very good. So that means we have one string here and one string here, and now we need to find out what a computer does. A computer takes a string here from the computer there, and it takes a string of 0s and 1s from the computer here, and then it adds those two, right? And isn't it a waste that all of you could have represented more different raisings of hands or bit strings than there are, let's say, grains of sand on Earth, except you did only one, right? So it seems that if just you had the possibility of doing like this and like this, which is not the same as this, that would be fantastic, right? And that is a quantum computer. So the idea is you have a black box, which is a normal computer, a string of 0s and 1s, and then something comes out, right? And now instead of these bits, takes quantum bits that can be both 0 and 1 at the same time, which means now it's also a black box. This black box is a little bit more expensive, but it's the same, essentially the same. I have 4 of these atoms on this side, which means they can combine to 16 different states, and putting it through that black box has done 16 calculations in once. That's not so impressive because they are fairly slow, but if we had 300 on this side, then we would have done more calculations than the atoms in the known universe. Which means take all the computers combined and let them run for 1,000 or millions of years, and it would not be the same as those 300 atoms. And that's why it would be nice to build one. What can we use such a quantum computer for? Maybe some of you have heard that they are very good at breaking the internet encryption schemes. So all the internet encryption, when you go to your net banking systems, that will break down. So that's not so good, maybe. But we also want to try to do some. Oh, maybe so you should think about that. So we have another encryption scheme. So whenever it's ready, don't worry, you don't have to close your bank accounts. But you should maybe think about that when you send something encrypted, it is out there, right? It is out there. And at some point, someone will have a quantum computer, and if they get whatever is out there, they will decrypt it, and they will know. Which means at some point, we will know very interesting things about you and other people who are maybe have more secrets. We also want to do something which is sort of more good for the society. And if you want to do something good for society, if ever you sort of want to make a big difference, go to one of these lists of the biggest challenges in the world. And if you can make an impact there, that's probably worth the effort. So one of the things that we think that a quantum computer can be used for is resources. We actually spend 2% of the energy consumption of the world producing fertilizer, because fertilizer can only be produced in a process which requires high temperatures and high pressures. But bacteria can do it at room temperature, and we don't know how. But if we had a quantum computer, we could sort of learn the difficulties or the mysteries of those and then find out. There's also something called a high-temperature superconductor, which we think can give sustainable green energy. Maybe there will also be CO2-absorbing batteries that will actually be able to pull it out So not only will it be a battery, it will also pull out the CO2 and fight global warming, and we'll also be able to design drugs in a much, much more personalized, much more efficient way. So those are sort of the grander schemes and the better sort of schemes. That is why everyone, all of the big universities, Yale and Harvard and Stanford and Aarhus, want to build a quantum computer. Right? And not only the universities, also IBM and Google and Microsoft are really trying to build a quantum computer. IBM already has a quantum computer, and it has 5 of these quantum bits. And they are saying they really want this year maybe to find something, develop it onto 20 of these quantum bits. 20 is not so high a number. I'm doing that because now I will reveal how many quantum bits we are working on having, right? And it's a bit number bigger than 20. So what we have is the coldest crystal in the world. It's a very small crystal. It is very, very cold, and it has sort of 300 atoms lying side by side. And if we could just turn that into a quantum computer, then it would be much, much better than what Microsoft can do. That would be fun. So it is almost a quantum computer because we have these individual atoms. We just need to sort of be able to control them, and we can send a laser beam onto each of the atoms, and then we can sort of flip them from the glowing state to the non-glowing state, which is very cool. But we also need to be able to pick up an atom and then move it to the next well. So the way we do that is exactly like this. We have a laser beam, and we shine a laser beam onto the atom, and the atom likes to be at the place where there's lots of light intensity, which means I move my laser, and the atom follows. But the atom is just like liquid. It is a wave, and what happens to a wave or liquid or coffee when we try to run and we're late for a meeting? We tend to spill, right? I was told not to do it, so I will not try to show it. But that's what happens. We run, and then it spills over. And exactly the same thing happens in our quantum computer. So we try to set our algorithms running and try to find various different ways of really optimizing the way there's no sloshing in the end, but they failed. So we did something different. We tried to develop a game, took that problem, put it in the form of a game, and allowed people around the world on the internet to solve them. So it looks a little bit like this. Here now you see this liquid-like substance. This is now what you know to be an atom. And this here is the container, which is the laser beam. And your idea is to sort of move it as quickly as possible to there without any sloshing in the end. And the idea is that this is very similar actually to water or to the process when we actually have a child on a swing. So maybe we have some sort of intuition that allows us to solve it more efficiently. And the idea is we have hundreds of thousands of people solving it. We have high score. Every time you play, it is recorded on our database, and we can take number 1 solution, and then we take the finger movements from your iPhone and use that to program our laser to make exactly the same movements. So in that way, your good solutions can be used directly in the lab. So here's one of the very biggest challenges that we have. Take one atom and put it on top of the other one, and none of them are supposed to sort of jiggle in the end. So I was very bad at this, but then at some point a guy sent me this, and so he was a taxi driver who told me then that he had only had 9th grade physics, and I thought it was really impressive that he found this, but it was even more impressive that he sent me sort of this text, this bit of text. And now if there are a couple of physicists, then you can read this, and we can actually translate sentence by sentence this into processes like quantum tunneling and excited states and all these things. So it seems as if this guy who has only had 9th grade physics, using the game interface, has rediscovered some of the laws of quantum physics that are really complex. So this presenting complex problems in the right way can activate a lot of our imagination. In Germany, it was called Taktik eines Taxifahrers. In Los Angeles Times, it was called Take That AI, because they thought that it was really fantastic that finally we were winning one of the battles against the artificial intelligence algorithms. So what is it that happens when we play these games and we produce good results? Has anyone played the game of Portal? Portal? Very good. So you know that in Portal is a game where you walk around, and sometimes you're supposed to do something which is physically impossible. So let's say I have to grab a bag and it's beyond my reach. So it's not possible to do this, but then I can place an entry portal here and an exit portal there, and then I fall out and I get to grab the bag. So what is happening there in games, and in many games, is that games allow us to change the rules of physics slightly. And what happens is that we have our normal intuition, and then we expand this intuition that we already had with an intuitive acceptance that maybe in this world we can have portals. Or in our game world, water can actually sometimes flow uphill, which is called quantum tunneling. Right? So we don't have to understand what quantum tunneling is, but sometimes water just flows uphill in that particular game, and I can make use of it. Right? And that's what games can do. It makes us imaginative. Okay, very good. So of course, we want lots of people to play these games, and so we have to create games that look exactly like your favorite game, right? So this was the maybe standard boring game here. Maybe you prefer something where a robot has fallen asleep and is now inside of a quantum computer and is sort of making optimizations. Or maybe you are sort of more of a cat person. I heard those people exist. And then you can control the way the cat moves by controlling the atom here. And when it becomes too sort of distributed around, then we have more of these cats. And at some point, you have to get the cats inside of the room that has milk. And at some point, you can actually observe the cat, and then you hope that it ends up with the one that is in front and not the one that is in the back. You could also play a game in which you sort of have a more sort of fluid-like game puzzles. If you are more of a literary type, then we are working on trying to create a novel which is revealed page by page by you solving the challenge. So you're rewarded that way. And then my son's favorite is this one here. You shoot spiders. And sometimes you run out of ammunition, so you have to reload your quantum gun. And if you reload it very well, then you will get quantum ammunition that kills a lot of spiders. And at some point you run out, and then you have to solve the challenge again. So what we're seeing here is us trying to motivate as many people as possible to play these games. So what is the basic idea that we want to do? We want to have very complex problems. We want to have people solving them. Then we want to use those to learn something about us. And learning something about us, maybe we can actually learn something about novel forms of artificial intelligence. If we have novel forms of artificial intelligence, then we'll solve some of the big challenges in the world. So what we did was we took a quantum problem and we coupled that together with a cognitive scientist, and then we called it Quantum Minds instead. So now Quantum Minds looks like this. It's almost the same game, except that now the rules of the game are defined by the cognitive scientist and not by us, which means you play this game and you have to play it 3 times in a row in order to win it. The cognitive scientist says that you have now learned it. So the last of these levels looks like this. Here are zones of death in which you always die when you try it the first time. And the computer algorithm also dies the first time it hits a zone of death. And the next time it also dies. And the computer algorithm then gets a score of 0, and then a score of 0 again, and has no way to know how to improve that score. Whereas when I observe all people playing it, they also die the first time, and the second time, and also the 10th time, but they keep saying, oh, I almost made it. Which means that we humans, for us, dying is not a 0 or 1, it's a continuum of almost dying, right? And this process of almost dying is extremely interesting to cognitive scientists. If we could find out how and why we know that we almost died, that would be fantastic. So that's what we're studying. How are we studying it? See, I just have to show this because this is the one time that I actually managed to do it. So we all have to look and see. Thank you very much. Okay, so I managed. So I didn't try that level again. So here you see lots of people who have played it, and here is their score, the number of times that they've played, and their score. The green people are the ones that managed to learn it in the end, and the black ones are the people who didn't. So what we're trying to do now is to predict the future. And predicting the future is actually not as hard as you think, or as unfeasible as you think, because what we do is we try to look at the patterns of the first half and see whether there's something, you could call it constructive or good learning going on. None of them have learned it, but maybe there's something in the way they behave that predicts that they will actually learn. And if we could do that, then we would have a predictor of how we should actually learn optimally. So this allows us to study the processes of learning. It's very complicated because if I had all of you in my lab and you were all doing it, then maybe some of you had coffee and some of you didn't have coffee and some of you were tired and not tired. So all of us are very different. So that's why what is called social science is very difficult. So that's why we have developed a game, and our mission is now to get everyone in the world to play it and then to create a cognitive profile of them based on their behavior in the game. So if you ever want to help us out by playing Tetris, then play our Tetris. Go to science@home.org and download the skill lab, and then you can play Tetris. And we are then trying to use Tetris or any other of these games as a predictor of what kind of cognitive types you have. And then we're trying to match that up with all the complicated data that we have, clean it up, and then try to infer something about us. In a grander scheme, what we are trying to do, we're trying to learn something about not only how we as individuals react, but how many people react together, collectively, how the society is actually constructed. So what we're trying to do is that we're trying to create, here's complexity, here's how the lab studies are normally done, and then we're trying to create sort of a continuum of games that are more and more complex, where we can study systematically across a very wide range of people problem solving. And then hopefully we can sort of infer something about how complex problem solving or societies are actually going on. Okay, very good. So we just have, I speed talked a little bit because I do want to get to this part here, this slide at least. So because I want to tell you how we learn something about us as people. Has anyone heard about Homo economicus? Yes, Homo economicus, right? So Homo economicus, we learned something about Homo economicus by games that are called Prisoner's Dilemma. It is a distribution game in which it's very similar to gas stations being next to each other, like this here. So the idea is that two players play against each other. They can either collaborate or they can try to cheat each other. If they both collaborate, they get 500,000 crowns each, right? So they get a high bonus, 5-5. But if one cooperates and the other one defects, the defector gets everything, gets 7. If they both defect, then they get 3 each. Okay, look at the numbers, add them up. And what should we do if we think collectively? If we think collectively, we should cooperate, right? 10 here must be better than 7 and 0, right? Okay, but let's think as Homo economicus, and let's now say, okay, I think that you will cooperate. What should I do to optimize my output? I should steal the whole thing and get the 7, right? I think that you defect. What should I do? I should probably defect, because if I cooperate, then I get 0, and here I get 3, right? Which means that the individual incentive is to always defect. Always defect. Okay, I will play a quick game with you. I need 2 volunteers. You two, please come up here. You will now get a happy smiley and an angry smiley, and we will now observe this in action. So you get an angry smiley and a happy smiley here. You are not supposed to see what everyone else. You get 5 seconds to think, and you play according to these rules, right? And to make it a little bit more interesting, there's a fantastic prize for the winner. Okay, fantastic prize for the winner. You get 5 seconds, and then you do like this with whichever one you selected, right? 1, 2, 3, 4, 5. Okay, 5. Okay, so we have 1 defector and 1 collaborator, right? So which means that we have a happy winner, which means you get to choose between a fantastic T-shirt which has Science at Home on it and a cup that has Science at Home on it. You want the coffee? He's a coffee drinker. Okay, very good. Give them a round of applause. Okay. So the idea that I wanted to convey here was that how much can we infer from that? 1 study, not a lot. And what happens in these cases is, when we study this, then of course we don't do, or social sciences, they don't do 1 study, but they do 100 studies. But 100 studies is not a lot, and that takes a long time. So what we want to do is take these studies and do hundreds of thousands of these. And we want to do them not only in Denmark, but also in China, because how we think about collaboration is actually very different across different cultures. And just to sort of tell you how this is how the Crown Princess and the Minister of Education play this. So they did collaboration, which I sort of forced them to do a little bit. So this just shows that we are constructing our society and our knowledge about how we would react as a large group based on these very, very small scale experiments that really cannot be extrapolated to that large scale, which is a problem for how we construct societies, right? So what we want to do is improve that data quality. That would be fantastic. Get everyone around the world to help us with that. But maybe if we dream big, we can do even better. So here is the last and my biggest dream. Create a virtual world simulator. So we would like to replace all of the massive online games, or at least one of them, have millions of people walking around in a World of Warcraft-like world, but created by scientists for scientists, in which we can study some of the biggest problems that we don't understand. For instance, there's a guy called Bernie Sanders, and Bernie Sanders said that you can take all of the Danish laws, impose them on the American system, and then you will have a fantastic system, which we have no idea whether that is true or not, because we have no idea of finding out how different systems scale with different system size. We have no idea how to do experiments on that. If we had a virtual world, we could do that. And don't tell the federal bank that I told you this, but actually they don't know what happens when they increase or decrease the interest rate. It is too complicated to know. So they believe that something will happen. It would be fantastic. Søren Pind, when I was saying this yesterday at the prize ceremony, he said, well, okay, maybe that is interesting. We should talk about that. There are really big gaps in what we could potentially know if we came together and all contributed. And that was my point. My point was that science is not a bunch of Einsteins. Scientists are not a bunch of Einsteins that think a lot and then have a fantastic and revolutionary idea. So my wife will sign that I am not a very always a very intelligent person, and sometimes seem very normal. And that is exactly how science is. It is normal people doing hard work of building on top of the knowledge that we already have, helping each other out. And by playing these games and helping out here, you don't get a Nobel Prize, but you help generate a little bit more knowledge for the whole of mankind, which I think is very noble. It is not just me, of course. So we need physicists, we need machine learning people, didactics, and cognitive scientists, psychologists, and all of us sort of come together and try to create the conditions that allows as many people as possible to take part in the scientific process of creation of data, which would be fantastic. I think if we all had a little bit more of understanding of the scientific processes, because then maybe we would not accept when there's a one-line statement like climate change is man-made, yes or no. Everything is complicated. Evolution is complicated, but that doesn't mean that having one small piece of evidence suggesting that not all of it is man-made means that none of it is man-made. Right? We can put higher standards to all of us and how much we demand to know about this, and that's what I'm trying to sort of teach. Okay, in the end, these are the people that did all of the real work, and I also want to thank sort of the people who were courageous enough to sponsor something so crazy as this. And thank you for your attention.